All right, excellent. Our next talk is by Casper from TU Delft, Monadic framework for name resolution and multi-phase type checkers. Casper.
Yeah, thanks. I'm Casper. This is joint work with Aron and Paul. And well, as the name suggests, this talk is going to be about name resolution and multi-phase type checking. In general, when we implement type checkers or programming languages, we actually typically need to resolve names in multiple phases. This may be something that you're not very used to thinking about because typing rules tend to abstract from this fact. They tend to abstract away the details needed to construct the necessary information that you need to type check languages. So for example, here is Featherweight Java. This is an excerpt from Pierce's Types and Programming Languages book. In order to define name resolution for Featherweight Java, Pierce says we assume the existence of a class table, and the class table tells us what is the structure of each class. And using this structure, well, we can define what it means to resolve a name. This is great for a declarative specification. We can read and we can understand how name resolution works precisely in Java. And we don't have to think about how this class table is being constructed. We can understand it completely independently. But if we are to implement a type checker, the order in which we fill in this class table is going to be very important for getting the semantics of name resolution right. Do we implement the right notion of name resolution? Do we implement the type checker that respects the typing rules, basically? And as it turns out, resolving names in general in type checker implementations does require phase name resolution. It requires you to construct this name binding information in a careful way, otherwise your type checker will be wrong. And to illustrate this fact, here is a Java program. We have a class A and an integer field x, and an inner class B, a class y that references the x that comes from the lexical context. Then we also have a class C that we're not using yet. When we initialize the inner class here, we are going to get 0 as the result because the x in the inner class references the x in the outer lexical scope. If we change this program to now use an extends clause so that the inner class now extends C, we have actually changed the semantics of our program. Name resolution is now different. The name x now resolves through this extends clause to the x down here. We can understand how name resolution works by alluding to a class table. So here's an example of a class table for Java. We have 3 rows in the table for the 3 classes that we have. The class table tracks what are the extends clauses for each class. It tracks what is the lexical context for each class so that we can resolve through that if we need it. And then we have the fields and the methods. And the reason why the x resolves through the extends clause is that, well, the extends clause for B has a C, and so C has a field x, and so we never resolve through the lexical context because bindings in extends clauses take precedence over bindings in the lexical context. So this is the name resolution for Java. We can understand it completely separately from phasing concerns. Now let's consider how actually not to type check this program. Let's consider what happens if we implement phasing wrongly and we construct this table in a wrongly phased manner. Let's start with a class table that has just 3 rows. We have a row for each class that the program contains. And then we just start filling in the class table as we go through the program. We start by looking at the class A. We fill in the extends clause. We fill in the lexical context. We fill in the fields, and actually as we encounter this field, we will also type check the right-hand side of the field initialization expression. So here we have just a 0, so that means that, well, that's trivially compatible with its type. Next, well, we proceed to type check the class B, and we inhabit a part of the class table related to this. And we're now ready to type check the right-hand side of our field Y. This right-hand side references an X. And in this broken type checker, I haven't filled in the part of the symbol table that has to do with the class C. So even though I have an extends clause that references a C, my class table is uninhabited. The fields are uninhabited for class C as of yet. And that means that I can resolve this X, and I will resolve this X even though I have a type checker that implements all the right checks, that looks in the class table in the right way. I have phased it in the wrong way, so the class table isn't complete yet. So this phasing error will not give rise to a runtime, a type checking error. I will actually resolve the name, but I will resolve it to something that is not the thing that I was looking for. I will not respect the name resolution semantics of Java. So this is a subtle class of phasing and name binding error. And the contribution of our paper is that we provide a framework for defining name resolution in type checkers in general, not just for type checkers that have class tables, but also for languages that have general scoping constructs, such as packages or modules, what have you. And then we provide a new approach to detecting and rejecting this subtle class of name binding error that I just showed you, where we silently resolve to the wrong thing. If we resolve to the wrong thing, our framework will detect and reject and notify the type checker engineer that something is wrong. You implemented your specification wrongly. And finally, we provide techniques that reduce the gap between specification and implementation. So using our techniques, we can write multi-phased type checker implementations, which is what you need in order to resolve names in general. But then there's a gap between that and the declarative specification, which does not involve phases. And we provide techniques that reduce this gap. So this is what you'll find in the paper. In the rest of the talk, I'll try to give a flavor of each of these contributions. To give you a flavor of this, the framework that we use is, I'll change the object language that we use. Here I have the same program as before, but now in a module language. I have a module A binds a field X, a module B that imports C. I have a field Y that references an X, which could either reference the X from the lexical context, or it could reference the X that comes from the import, exactly as before. The framework that we provide in the paper is based on scope graphs. So what a scope graph is it is essentially a data structure for representing name binding information. Whenever you have, it's going to contain the same information that is in a class table or a module table or a symbol table that you may know from compilers. But it's going to lay out this information in a graph. The observation here being that actually when you have a class table, it contains cells that reference each other in a way that really represents a graph. And if we represent it as a graph, we can represent name resolution as a graph search problem. So this is the idea behind scope graphs. And I'll now give you a flavor of how scope graphs work. So we will type check our simple module language here in 3 phases. The first phase, we will just look at the modules and the members and construct the scoping structure of those. Second phase, we will resolve the imports. And in the final phase, we will type check the right-hand sides of definitions. So we start by just considering the first module that we have. This is module A. This constructs this piece of scope graph over here, where circle nodes represent scopes. So here we have a root scope, which has a declaration for the A module over here. This declaration is associated with the scope of the module, so that whenever we resolve to something of type A, we can access and we know what is the scoping structure of A. So A in turn is also a scope, the scope SA. It has a single declaration for the single field that A binds. And we have an edge that connects the scope of A, the scope of the module, to the lexical root scope, which makes all the bindings that are reachable from the root scope are now also reachable from scope SA. So this way, by connecting the scopes, we can really model visibility and reachability policies. Proceeding with type checking, well, we do this exercise for all of the scopes that are, all of the modules that are in this program. So the next module to consider is module B. Again, we create a new scope for module B. This scope has scope A, the scope of module A as its lexical parent. We get a declaration for the module B inside of our module A, and we get a module member for the scope of B. And finally, for module C, well, it's the same idea as before. So that was phase one. We've constructed a part of our scope graph. We've constructed the part of our scope graph that just considers the modules and members. In the next phase, we are ready to now start resolving imports. Now we know what all the modules are and what their names are, and now we can resolve named imports. Here we have a named import that is referencing something by the name C. Well, in order to figure out what this C is, we have to do name resolution. We have to resolve the name C, and assuming we've constructed enough of our scope graph, which we have, we can resolve the name C. And the way we resolve this name is as a search through the graph. This search through the graph is basically saying, well, we have a query here, which says we are looking for something starting in scope, the scope of B. The thing we're looking for is a C. And then the path that we're looking for through the graph should have this shape. We can follow lexical parent edges. We can follow a single import step, which defines the name resolution policy of this language that we've defined. We are allowed to follow a single import step, and then we should be able to find our name. And then, we should find the module. The last argument that we have here is an ordering predicate, which allows us to compare paths. So if we have multiple possible ways of resolving the same name, we can decide which name we prefer by looking at the paths and comparing them, and basically implementing name shadowing in this way. In this case, well, the thing that C resolves to is the C down here. So what we do is we add an import edge in phase two from the scope of B to the scope of C, such that all of the things that are in C are now reachable from scope SB, which is how imports behave. And now we're ready to finally type check the bodies of our definitions. In order to type check the two x's, well, they're trivial because they're both ints. So the interesting case is the case for the y here. In order to type check the right-hand side, well, we have to resolve this x. Again, we perform a query through the graph, and we figure out that there are actually two ways of resolving this x. And our ordering predicate, which I haven't spelled out, will prefer paths that traverse import edges over paths that traverse lexical parent edges, thereby implementing the right name binding policy for our language. So all that I've shown you is basically standard scope graphs. This is all based on previous work. A new thing here is that we have embedded this in Haskell. We've embedded it, this is why we call it a monadic framework. We've embedded it in these four operations. We have a new operation for creating a new scope, an edge operation for creating a new edge, sync operation for creating a declaration, and a query operation for querying the scope graph. This is all you need to do name resolution in any programming language, really. What I haven't talked about yet is how does this help us with this subtle name binding error, this subtle phasing error that we considered in the beginning of the talk. So actually our four operations help us detect and reject subtle errors, like the one I showed you earlier. So to illustrate that, let's consider how we can type check our program again by not using three phases, but just using some differently phased approach that will resolve names in the wrong way. And then how this will allow us to actually detect and reject this kind of phasing error. So we start by type checking module A. That will create the module structure of A, exactly as before. Next, let's say that we actually type check the right-hand side of our definition. So here we type check, well, 0 is an integer, boring. Moving on, we type check the module B and create the scope graph structure for the module B. And we don't resolve the import of C just yet. Instead, we start type checking the right-hand, we start type checking this definition down here, and we start type checking this X. So this is exactly the same problem that we had with the class table example from before. When we query the scope graph is incomplete. The information that we have about a program is incomplete, and so the X that we resolve to will be the X from the lexical context. This is the wrong resolution of X. The way our monadic framework works is it will actually allow this for now. And then later on, when we add the import, we will detect that the import was added and a new path becomes available, and we will reject the program. So let's continue and see when this happens. We start type checking module C. That will create the module structure of module C. And then finally, well, we'll type check the right-hand side of X as well. Finally, we are ready to start resolving the import C, which when we resolve it, well, we figure out that this is the C that we want. We add an import edge, exactly as we did before in our graph, which makes all of a sudden a new path available for the previous query that we ran. The previous query for X, which before resolved to this thing, now actually resolves to this thing. So dynamically, during type checking, our monadic operations that we provide for scope graph construction, check whenever you add new structure to your scope graph or to your class table, if you will, to your symbol table, whatever, you check, does this violate previous resolutions for any of the names that I knew about? And if it does provide new paths that shadow the old ones, we raise an error, and the type checker engineer can now know that there is a problem in the program. It doesn't silently return the wrong thing. We will reject this program as containing a phasing error that is really in the implementation of our type checker. All of this happens behind the scenes in these 4 operations. So all you have to worry about when you're programming against our interface is you have to know that these 4 operations construct scope graphs. And whenever you make a query, you can be guaranteed that the query is going to be stable in the final graph, or you will get an error notifying you that you have made an error. So you can sleep better at night. Okay, so that was basically the second contribution point here, a new approach to detecting and rejecting phasing errors in type checkers. The final the final contribution that I have here on the slides is that we provide techniques that reduce the gap between declarative faceless typing rules and multi-phased type checker implementations. So using the operations that I've shown you so far, I can write type checkers that could look something like this. This is a type checker for the module language that I showed you before. Here I'm using a top-level orchestration function for first creating a lexical root scope. That's the first line here. Then I'm calling a modules function which represents the phase 1, which will create all the module structure, the scoping structure of my programs, and postpone the type checking of imports and the type checking of right-hand sides of definitions. So I will get 2 queues, 2 working queues representing these delayed constraints. And then I can first do the imports in phase 2 and then finally do the members in the final step. So this is a fine type checker. It will behave exactly as I intend. But it's not at all obvious how this is connected to a declarative specification that I could write for my module language. So here is a declarative specification using scope graphs shown on the right here. A module here is well typed according to this typing rule. Whenever I have a module scope that exists in the graph, that's what this nabla here represents. By the way, these typing rules are borrowed from previous work on this module that describes this module language. And if in the scope that I'm in, there is a declaration for the X, and if my set of module members are well typed under my module scope, then the program, then my module is well typed. So each of these rules do not talk at all about ordering. They just talk about the scope graph having the right shape, just like the featherweight Java rule that I showed in the beginning talks about the class table having the right shape. And the question here is, how does this relate to this very explicitly phased implementation that I have on the left? In particular, one of the challenging rules here is that actually for this def rule here, I said that in phase 1, I actually want to construct the entire scoping structure of my module except for imports. Well, that means that this constraint should really be run in phase 1. And this constraint checking that the right-hand side of a def is well typed should only happen in phase 3. So my premises here are scattered across my type checker. There's a gap between the specification and the implementation. I won't have time to go into all the details of how our framework works, but a key ingredient that we provide in helping bridge the gap between specification and implementation is that we use applicative functors. So all of the definitions that I've shown you so far, we're using monads in Haskell. So that is that we're using these two interfaces summarized up here. We are now going to be programming against a slightly richer interface. We're going to be programming against an interface of applicative functors. Here I've phrased that as monoidal functors. It's equivalent to what you'll find in Haskell as applicative functors. We're going to use functor composition, again, a standard definition that you'll find in the Haskell standard library. And then we're going to use these slightly less standard combinators for phasing computations. The here computation says if I have a computation, a phase one computation, I can treat that as a multi-phase computation where F is the first phase and G is the second phase. And there can be used to inject a computation in phase two into a multi-phase computation. And then I provide these custom bind operations here, which allow me to compose multi-phase computations. So the first one here says, well, if I have a phase one computation and I have a phase two computation that depends on the value of the first computation, I can combine them into multi-phase computation. And this second one says, if I have a first phase computation and something that has a multi-phase computation as a continuation, provided F is a monad, I can combine these. So these are the combinators that we use, that we provide for now programming type checkers in a slightly richer way that lets us define and compositionally map abstract syntax trees directly onto their typing constraints. So again, I won't have time to go into all of these cases. The main point that I want to make here is that whereas before I had typing constraints that were scattered across different functions in different phases, I can now say precisely in each case of my type checker that this abstract syntax tree has these typing constraints, and then I can use my monadic combinators, my applicative combinators, to specify precisely the order in which these different constraints need to run, and compose them in a way that respects the phasing order. So this is all based on it's inspired by previous work by Gibbons, Kidney, and Schrijvers and Wu. But we have a spin on it. For the details of how this works, well, you could ask me but I think it's better to perhaps look at the paper. So in the paper you will find more details of how and why this works. You'll also find two case studies. The first case study is for LM, the simple module language that I've shown you. And while it may look like a very simple module language, it actually has a very sophisticated import feature that has import-sensitive name resolution. That means that whenever you import something, it may affect previous imports. While this sounds like a contrived and challenging feature, it is actually a feature that turns up in a microcosm version in the Rust compiler, which does name resolution in a way that is very careful to phase the imports in the right way. It's also a feature that previous work on scope graphs was unable to express. So previous work on scope graphs on the meta-language statics, which allows you to basically derive type checkers from rules that look close to this. That meta-language is not able to express this case study that we are able to express with these combinators. The second case study that we provide here is for the Mass-Hindley-Milnor type inference, which is another example of a feature that was unknown how to type check with statics, this previous meta-language. It does not involve phasing per se, but it is important that you only do unification and generalization in a particular order. You can only generalize over type variables once you know that you've fully analyzed the lexical context that you're generalizing over. That's all. Happy to take questions. Thank you.
Yes, thank you very much. A very nice explanation of the symbol resolution and the potential conflicts. I'm curious about the dynamic typing, where you explained that, well, you first kind of accept a solution, later when the scope graph is completed, switch it again. So comparing to traditional programming languages or even the typing system or symbol resolution of language workbenches for modeling languages, there I would expect something like, well, we have these different phases first, build up the complete graph, and then do the resolution. Compared to that, where is the benefit? Are you more efficient than that because you can dynamically load it, or do I have to care less about my phasing? So just compared to first constructing the whole graph, because then I, of course, should be able to come to the same result.
Yeah, so our goal here is really to try and bridge the gap. It's a twofold goal. We want to try and bridge the gap between specification and implementation. Right? We have typing rules that define our language, and then we want to bring an implementation as close as we can to the typing rules, and while also being as flexible as we can. And we provide added flexibility over previous work on statics. If we are to construct this full graph first, you are basically implementing a completely phased approach, where this graph, I don't know how that would correspond to your to typing rules. Would you then, you are probably going to have typing rules that then would talk about the graph being fully constructed, and you would have phases in your typing rules. And I would argue that that's actually an anti-pattern, and that phasing is an operational concern that we should be abstracting from in typing rules. So I don't know if that answers your question.
Yeah, it answers the question. It was my guess that you should care less about the phasing.
Right, right.
Okay, thanks.
Thank you. A clarification question with possibly a question after that. So when you are really resolving already, so in the last phase, in your query, can you also put some type in information about the thing that you are resolving, about the, for instance, the context of the thing that you are using? I'm thinking of some languages like 4GLs where name per se is not a unique thing. You can have multiple things with the same name, but as long as their types are different, then you will be able to resolve it. So you need to look at the place where the thing is used, infer whatever you can from the type, and then you your starting of a guess is enough to resolve it in the table. Can it be done here?
I think it can be done. I would be happy to try it out and brainstorm a bit more in a break. Basically, the query operation that we provide just says, you give me a declaration. I don't care what the declaration is. You give me a predicate that identifies this declaration. So you can write that declaration, you can write this predicate in any way you want. You can write it to do fuzzy matching on both the name and the type if you want. So in principle, that's supported. And you can also have, these are monadic constraints. You can have backtracking in your monad if you want. Actually, for implementing LM, we do a limited form of backtracking. So I think yes.
Okay, cool. Then I do have a follow-up question, which is, you mentioned that this particular implementation can handle a case study that was not possible to be handled a couple of years ago, when it was also made sort of this soft claim of scope graphs can do everything probably. So now they can do even more, and it's probably everything, but probably. So what else is there that prevents us saying that scope graphs of this particular form can do everything?
That's a good question.
Sorry.
So, yeah, well, so I think that the claim that scope graphs can do everything, I think I will stand by that. You can emulate typing context, right? So anything you can do with the typing context, which is the main alternative, or anything you can do with symbol tables, you can encode that as scope graphs. The thing that you couldn't do in previous work was that, well, we had particular constraints in place because we wanted a declarative specification. Here we're giving up some of that declarativity and gaining a lot of expressiveness in return. So the model is the same, the implementation details are slightly different. It's striking a different point in the design space, putting more responsibility onto the type checker engineer, responsible for actually facing things in the right way, but at least telling him or her if they get their facing wrong. So this is sort of the trade-off. This is the reason why we're striking a different point in the design space, I think. Don't know if that is an answer in the right direction of your question.
It's a step.
Okay.
Thank you.
If you're looking for another challenging case, I recently had to implement name resolution for Ansible infrastructure as code scripts. And over there, you can actually, if you go to your conclusion slide, you had the example. There you can actually, or the module language.
So
Yeah,
this one?
just the conclusion one, no, the two thumbnails.
Yeah.
So within module C, there you could actually replace the def keyword for x with a set fact keyword, and all of a sudden that would take precedence over any other local variable declaration. So would that be supported in the queries? Because it seems to me you would need some kind of negation then in the query language.
I think so. I think it can be done. Again, in order to actually implement this import resolution semantics, what we did was we implemented backtracking, where we sort of roll back, we speculatively add some things to the scope graph, and then it may turn out that that was not the way to do things, and we roll it back and we try over. So this backtracking is compatible with the monad because we are now working in this monad more abstract setting. We have more control. And so I think that you could implement the right control operations that lets you control the scope graph construction. The question is, what are the right operations for this particular feature? And I think that's an interesting question that I don't have the answer offhand to.
It's a nice challenge,
Yeah,
I think.
yeah.
All right, I would say let's thank the speaker, but I have like a bunch of questions. So look, the thing about being a session chair is you don't get to ask your questions because you want to sort of defer to the audience. So I will hound you later, especially like what was it, weekly critical edges, what was that, how does that compare?
Yeah.
But anyway, let's thank our speaker.
Okay.